Hi, and welcome to the Engineered Mind podcast, a podcast about engineering, AI, neuroscience, and other interesting topics of life to educate and inspire people all around the world. I'm your host, Jousef, and for this podcast, I welcome Wolfgang Gentzsch. Wolfgang is co-founder and president of UberCloud. Together with Burak Yenier, he founded UberCloud in 2014 to develop novel HPC technology to move complex engineering simulation workloads to the cloud. Previous assignments were in grid computing, for instance, dgrid, DISA, OIDAT, NC State Grid, and Sun Microsystems. He is professor of applied math and computer science, working as a scientist at the Max Planck Institute and as a head of CFD department at the German Aerospace Center, and he founded several companies in the parallel computing sector. From 2004 to 2008, Wolfgang was a member of US President's Council of Advisor for Science and Technology, short PCAST. And now, ladies and gentlemen, here's my conversation with Wolfgang Gentzsch. Welcome, Wolfgang, to my podcast. It's a pleasure to have you on my show. Maybe, as always, we'll start with a brief introduction. Maybe you can do that yourself because you know yourself the best.
Yeah, almost. Thank you so much, Jousef. This is really kind of you to have me here in your postcard series. And sure, I see you are working from home. Same here. And we are lucky in that we have a job which allows that. So let's make use of it, right? A bit back to me. I'm the president and co-founder of UberCloud. UberCloud is a cloud service which helps engineering users to move their complex workflows, simulations, etc., to the cloud, such that the user can switch between on-premise and off-premise, meaning cloud, HPC cloud, engineering cloud, in a very seamless way, at least at your fingertip. Within 1 second, you can switch back and forth. I founded UberCloud together with Burak Yenier. First, it was a project in 2012. But we can. That's a nice story. So we can get back to that a little bit later because it's just a short introduction. Okay, and please stop me if I'm talking too much and too long. Right. So that's one of my challenges, my personal ones. So, okay. People call me a veteran in HPC. I started already almost 40 years ago with my diploma thesis, PhD, and then several stages of research scientist, leading the CFD group then at the DLR, the German Aerospace Center in Göttingen, and then founding several companies. One of them, Gridware, I sold to Sun Microsystems. With the baby of it, which is Sun Grid Engine, later on Oracle Grid Engine, later on, and finally Univa Grid Engine, a workload resource manager. And very close to what I always did, namely loving, basically challenging applications, engineering, scientific applications, which always needed high-performance computing and whatever concerns high-performance computing. So that's where I feel home. Mm-hmm. Then for Neumann machines, systems, over to vector machines, like I benchmarked one of the very first Cray computers, then over to parallel systems, to grid computing, finally to cloud computing. Seamless transition. It was nicely evolutionary. So nothing to learn from scratch. The very first one for Neumann was from scratch, but then the computer architecture just evolved. And several projects, more companies, and North Carolina Supercomputer Center, and then dgrid, DISA. We can get back to that later. EU.DOT, finally founding UberCloud together with Burak Yenier. And let me mention that as well. So Burak, in 2012, he was vice president of operations at Fiserv, a financial services company. He was very familiar with cloud already, while I was quite familiar with high-performance computing and engineering simulations. So this came together beautifully. And now we work together already. Oh, let me think about that. Oh, yeah. Oh, it's basically exactly 8 years now. So, okay, so I'll stop here.
To the day. That's great. So what I know from you is also that you have something called a Docker container, a software Docker container, and you developed several layers in UberCloud over time. Can you maybe explain what a container is, for instance, for our listeners who are not familiar with a container, and how this developed over time?
Yeah, so I guess most of the audience will be engineers. So I describe it more like high level. Mm-hmm. So containers are not really new. The first ones I remember, they were in Sun Microsystems operating system, Solaris. So they already had containers to basically host the engineering flow. Like from pre-processing, solver to post-processing. Everything, you take the whole bunch, you don't touch it, which is so you don't have to port the application really onto a new system or even a new cloud or so. But you take it as is, you put it in the container. But these containers, they are similar to virtual machines and much more lightweight, meaning that a container doesn't contain the operating system. It sits basically on top of the operating system, while VMs, they also have what they call a hypervisor, which is a very powerful glue sitting between the system and the application. So the container is really lightweight. So the difference is really that containers don't consume performance, while VMs, they do. The hypervisor, especially during I/O operations, need a lot of performance and lead to not really scalable performance. Then scalable, I mean, more and more cores, usually getting better and better performance, faster time to solution, etc. So these lightweight containers were originally built, these containers, for microservices. And we took them in 2013 and developed layer by layer by layer on top and turned them into basically HPC containers, full-blown HPC machines, so to speak, which, layers have a virtual desktop. They have, they talk to GPUs, also MPI, parallel computing layers, and layer for InfiniBand, and many more. So that when you port your application within the container then to the cloud, the application container then is able to make use of the whole high-performance computing, also, the supercomputing environment. So, Okay.
Can you maybe also talk about that UberCloud is specialized in HPC, meaning, and also going into a little bit into depth what on-premise means, hybrid, as well as on-demand, because you combine several models, so to speak.
Mm-hmm. Yeah. So, that we focus on HPC is not a secret.
Yeah.
Looking at our history and of our people's history, of our employees, engineers, scientists, physicists, etc., etc. Also, when we started in 2012 with the UberCloud project first, we figured out that the enterprise side, they are already in the cloud at those days. right? They are really used to work with cloud already. Amazon started its cloud in 2006 already. And however, in HPC, it was completely unknown and also debatable. Many people said cloud can never be suitable for HPC because of the very specific high performance. And in those days, it was true. Right? But we thought, give it a try. And we worked with hundreds of engineers then between 2012 and 2014 first to evaluate how suitable the engineering applications are for the cloud and vice versa, how suitable the cloud is for the HPC applications. And we developed case studies, published them, and we developed compendiums, annual booklets with 20 case studies to educate the community, right? To help the community to better understand the HPC cloud and the benefits, but also the challenges. With these over 100 case studies in the very first 2 years, we learned especially the challenges. And we can talk about this a little bit later, but that helped us then to develop the perfect container for high-performance computing. So back to your second part of the question, which was about on-premise, hybrid, and public cloud. Then our containers run on every kind of cloud. Right? So public cloud, obviously, Microsoft Azure, Amazon AWS, Google Cloud Platform, etc., etc. That is all public cloud. Private cloud is usually a powerful server, which with the right middleware layer, then on top of that server, is able to provide computing as a service to the company users or to the organization or research organization or university users, right? As a service. Right? Very similar to the public cloud service. And that's why we usually call those private cloud or on-premise. And then in between now, we have built architectures for our customers, large and small, which combine both. And there is an intelligent scheduler on top, which decides, according to your requirements, if a job goes on-premise for like security reasons, intellectual property and compliance for within a company, and or the scheduler says no, that can be run outside in a public cloud. Very balanced utilization of now more and more resources. You are much more flexible. You can be much faster. Instead of 10 simulations, now you can do 100 if you want, and can do careful parameter studies, which lead to much better quality of product then by testing, simulating different materials, for example. And you can shorten time to market for your next generation product, for example.
That makes absolute sense, yeah. Can you maybe talk about the distribution model somehow? Because you work with a lot of partners like Ansys, Dassault System, and I really like the model that you use because it's basically something like a library where you have a shelf and you can simply pick what you need from that shelf. Maybe you can explain a little bit more accurate way.
Yeah, that's nice. Yeah, Jousef, that's a nice question, because now you give me the opportunity to demonstrate how powerful this technology is. A container is also something which you package once, and then you can use it everywhere. It's really amazing. So we package, ANSYS 20.1 and put it on the shelf. Right? And then when there is a customer request, then we take it and we move it to any kind of computing resource that the customer wants. And as soon as this application container, this ANSYS 20.10 container, is plugged onto the cloud server, the user automatically out of the container, we don't touch it, right? It's fully secure. So out of the container gets saying, hello, welcome, Jousef. Here is your login and password. So you click on your login button, and then through your browser, you get taken to your container, to your application workflow container. Type in the password, and then within a second, you're in the container, and you recognize your existing workflow. It looks identical to what you have on premise, on your workstation. So there's no learning needed, right? It is what we call cloud with one click. Yeah? And then you can seamlessly, take your data, move it over into the container, seamlessly continue doing your job, right? Without any difference, but sitting on much more powerful resources.
That's interesting. Also, you mentioned the point secure. Now, people nowadays, when they switch to cloud computing, they always have this fear that cloud computing might not be secure. Can you maybe go to that point and explain how security is taken into account in these systems?
Obviously, it's a very good question. Also, it's a question which is 8 years old, right? That was one of the first questions our very early engineers were concerned about. Because at that time it hasn't been proven, right? It was not in-house, okay. Despite the fact that the in-house data centers are attacked much more often than the cloud centers. I mean, if I want to steal a turbine, I don't really go to Amazon with 20,000 customers at the same time and looking around. So where is a turbine, right? What I do is when I go to P&W, right, and break in and find it, right? So that's why company data centers are much more vulnerable because I know exactly where to find it, right? And I have the best hackers in the world behind me, so I can get everything. But in the cloud, it's really cumbersome. So, okay, that was number one. So number two is these big cloud providers. They fulfill all major security compliance demands, and they are certified for each of these different security compliances. And so that's underneath. So now you have to build something which maintains and uses this secure environment and doesn't jeopardize it. So meaning the containers have to be secure as well, right? So now it's getting a little bit tricky, and I apologize for that. Containers have one vulnerability aspect compared, for example, to virtual machines. A sysadmin can have root access, right? Even a user can have root access, which theoretically allows someone who sits in a container, and his container could theoretically go through the system into another container. But the good news with our implementation is our containers are sitting on a dedicated server. So if a user requests 16 compute nodes, the user gets 16 compute nodes, and the containers are sitting on these secure 16 compute nodes. There is no way that someone else can get into the same system. It's a dedicated system for that specific user. Mm-hmm. So root access is no point of concern anymore. Right?
I get it.
So in addition now, as I said before, the user as soon as the container is sitting on the server in the cloud, the user gets automatically an email, a welcome email with login and password. So it's like a rental car. Right? You have the key, and you and only you, as long as you have the key, can access and drive the rental car. And you pay per use, right? At the end of the usage, you give it back, you pay with credit card or whatever, and then you're done. The same here. We have developed an environment which is fully automated and self-service. So the user comes in, requests a certain cluster of, say, 16 compute nodes, and within a few minutes, really a few, 3, 4, maximum 5 minutes or so, the whole cluster is built up automatically according to some technologies. Is built up, and as soon as the cluster is ready and the ANSYS 20.1 container is moved onto that cluster, the user gets the welcome email with login and password, and now working on the whole fully secure stack.
Mm-hmm. Thanks for this nice explanation, Wolfgang. What I want to touch on is also you mentioned this nice analogy with the rental car. Now, a user can also choose an older rental car, so to speak, and it can use an older version as well, which are in the shelf, right? So let's say he doesn't want to use ANSYS, let's say 2020 version, but the 2050 version, 15 version, for instance. That's also possible, right?
Very good. Yes. We build containers now since 2014. Right? So the oldest production container we have on the shelf is, in fact, OpenFOAM. OpenFOAM is from 2014, but the first commercial container, in fact, it was kind of crazy to the next step take such a big software. Is ANSYS 15 right? From 2015. And since then, for every year, we have 2 to 3 versions of ANSYS 16, 17, 18, 19, 20 already sitting on the shelf. Altogether, we have almost now 300 different containers sitting on the shelf, right? Ready for a customer. Someone who wants to repeat a simulation, which she has done like 4 years ago. Yeah? She tells us, we upload that 2016 container, and then she can do or repeat simulations which she has done like 4 years ago. Yeah.
From what I understand, and I've done a little bit of research about UberCloud, basically, when we take also SimScale into account, for instance, the main focus there is small and medium-sized enterprises, so short SMEs, and you are more for specialists, if I'm allowed to say that. So you shouldn't be a beginner, right, in simulation. If I use UberCloud, for instance, maybe you can explain that.
Yeah, ideally, even for SimScale, your users are usually not beginners, right? And it makes life easy. If I know OpenFOAM quite well, even as an advanced student, right? You learn that, at the university. You are not a beginner, right? And you can really use the high potential of the SimScale platform, right? However, this is really young. You said it nicely. So it is a canned service. There are simplify it, small, medium, large packages which you can subscribe to. And usually what your users are doing, SimScale users, they come on the platform, they do a simulation, and then they go away, right? Until they do a new one, or they modify a parameter, they come back also. So what we do is what your guys, David and others, have done in the past. They have built this environment as a service infrastructure, as a CFD service infrastructure first, and then they added a finite element infrastructure or service as well to that. So that's what we do for what we call Fortune 5,000 enterprises. So we are really focused. That's why we are nicely complementary, our two companies, right? You are doing the real on-demand service, while we are doing, basically we are rebuilding the Fortune 5,000 companies in-house environment, in-house HPC environment. We are kind of rebuilding or extending it into the cloud seamlessly. So they don't have any clue. At the end of the day, the engineers don't have any clue where their job is running. Some intelligence decides, okay, this job has to go inside, this job has to go to cloud. And there are usually three major components, if I may say that, of such an architecture, right? We encourage the customer still using their on-premise environment for quite a while. But I mean, we already see that they successively reduce their in-house resources for the benefit of using cloud resources then, which they are successively ramping up. But it's a nice, seamless transition, an evolution from the on-premise then towards the public cloud environment. And these three components, therefore, are on-premise, as usual, and then a hosted environment in the cloud, which is a fixed cluster, which we calculate according to their average utilization, to their average use. Right? So that this cluster, this hosted cluster, then can stay up and running, because then you can use reserved instances, which are much cheaper than on-demand instances. Right? So if you sign a contract for 1, 2, 3 years with the cloud provider, you get a very steep discount on that side, on the hosted side. So it makes a ton of sense. But it should be ideally mostly almost fully utilized, right? To make it really efficient, price performance wise. And the final component is then really the on-demand component, which is one of the users of this company goes to the service platform, requests a cluster of 16 compute nodes, for example, and then within a few minutes, that cluster is built up. His favorite software, Star CCM Plus or whatever, is moved, or OpenFOAM, okay, is moved onto that on-demand server now. Then simulations are done. The user shuts it down completely. Data is saved, usually stored in the cloud for reuse, for example, or for post-processing further, etc. And the server then is shut down.
Get it. Maybe just to explain for the audience who might not be familiar. So the Fortune 5,000 are those who get between 100 million and 1 billion in annual revenue. And you are also covering...
It's 100 billion.
100 billion, sorry.
No, don't worry. I mean, our three biggest customers, for example, these days, are among the 10 largest companies in the world.
Yeah, that's what I wanted to mention next. Good that you said it. That's good.
Oh, okay. So,
But also now in these times, I think your UberCloud especially makes absolute sense. Like if you work from home, for instance, you don't have to go to work on your workstation, which is kind of limited in terms of nodes and computing power. You can just log in, take that one you want from the shelf, to use the analogy again, and work with that, right? So it's quite comfortable, I would say.
Yeah, so that's a very good observation. And we recently have encouraged our customers to make better use of that. There is no difference between, when you look at the hybrid environment. So on-premise, public cloud, and the combination of it, there's no difference between working from your office or working from your home. I mean, both ways, you go over the internet, you have a secure connection very often, and then, you do what you're used to do, what you're familiar with, right?
Can you maybe walk us a little bit through roadblocks in HPC? What are the biggest bottlenecks in HPC?
Yeah. So let's cut it in two pieces. Let's look at HPC first, and then let's look at HPC Cloud, right? Because then there are additional roadblocks coming and being very typical for cloud. But HPC itself has roadblocks. And that's why we, in our community, which is the HPC, high performance computing, and the CAE community, computer-aided engineering, basically the simulation guys. HPC roadblocks, it's very clear who has worked on HPC for a while. HPC as such is a complex beast, right? The software, the application software, to make really use of the power of an HPC system or even a supercomputing system has to be fine-tuned to the architecture underneath, which is really annoying, right? My very first, and when we prepared this conversation a little bit like a few days ago, we had this nice chat. So my very first computer was a von Neumann machine, right? At the Technical University in Aachen. Then my first language was Algol. You never heard that? I
heard it, but I never used it.
No, okay. But that was von Neumann, a completely serial machine. We can't go into detail then. But the next big step then was vector computers. Then in a sudden, CAE research brought out their first CRAE-1 and CRAE-1S. And I was very lucky to being involved then in the evaluation of the first supercomputer at the Max Planck Institute for Plasma Physics in Germany then. And the second one was the CRAE-1S, serial number 11. I still remember that one. The CRAE-1S at the DLR, so the German Aerospace Center in Göttingen. And by the way, I mean, I promised you to dig into that book.
Yeah.
So that's from that is the one which we talked about. It has algorithms, numerical algorithms for solving large systems of algebraic equations, discretizing partial differential equation systems, nonlinear ones, etc., etc. Taking them from serial machines to vector machines, from serial to pipeline architecture. And together then, the second part of that is contributions from 5 of my then colleagues who described nicely how they then did the vectorization of their specific CFD solvers. So that was that was that one.
Yeah, it's quite of interesting.
Okay, and then
sorry, Wolfgang. It's quite of interesting that you mentioned, because you just use these simple terms like HPC and vectorization and so on. But if you go down in the architecture, like memory-wise, how complex it actually is, it's quite fascinating that you have to make sure that the memory is allocated in a way that it's useful for the machine to actually use it. Like, having chunks in the memory and then just use this chunk and work with it. It's quite of interesting.
Yeah, I mean, you're talking about the memory banks, right? So you have memories with 16 banks, because when you take a data out of one bank, then you cannot immediately take a data out of the same bank or out of the same memory. So because then, okay, next bank, and at the end, after 16 banks, now the first bank is available again, and then you can grab the next data. So that's why you want to have the data. It's a continuous data flow, and we did that in macro assembler. Okay, so sorry for that.
That's
I don't want to confuse.
Yeah, it's very interesting. What was for you when you started?
After that, because you were talking about the challenges, right? Because and that continued, got worse. So sorry to continue here, because we were not even halfway. The next one was parallel computers, right? and then massively parallel computers. Send, receive, blocking, non-blocking, and all that good stuff. We did that all manually, but because it was seamless, we were not really aware of the increasing complexity. And after that, we were grid computing, and I founded my company Gridware, which then I was very lucky that Sun Microsystems bought it, and I moved over to California. One of my greatest times I had then to working in this very innovative environment of Silicon Valley. That was amazing. Okay, but I got back and took over dgrid, the German grid initiative, connecting over 20 different research centers in Germany into a grid. Later DISA, distributed European infrastructure for supercomputing applications, connecting, I think, 14 different supercomputer centers in Europe within one grid. Basically, these are already predecessors of cloud services for researchers, because researchers had a portal, and seamlessly they went to a computer which was suitable then for their application and had available resources and so on and so on. Okay, so now I stop here.
It's great that you talk about the past. It's kind of for younger people, it's super interesting, like talking about these kind of things.
No, it is. Yeah. It's even for older people, right? It's still interesting.
A bit older people. Let's say it like that.
Oh, yeah. Oh, very nice.
What I want you as an expert to talk about is a bit the difference between GPUs and CPUs, because we know, for instance, if you are a gamer, GPUs are quite interesting, and you have these graphic cards and it's kind of fancy. Can you explain what the difference is and how you use that for your advantage?
Oh yeah. Again, I try hard to not go too deep, but when you look at graphics, right? You see a screen in front of you, and it's 1,000 by 1,000 pixels. So every frame. And you need about 30 frames per second to have a real film experience, right? But these are all arrays, right? These are big arrays, and in mathematics you could map that to a matrix, right? And so moving things within that sequence then means you have matrix times vector equals vector, and this all the time. And we had these parallel computers in the early days as well, right? So the array processors are big array machines. I forgot the name, but doesn't matter. Yeah, there were about a handful of these array parallel machines, so they are able to process in parallel, right, smaller chunks of these, like 1,000 by 1,000 frames in parallel, right? And if you have 1,000 of these processors, then you were 1,000 times faster. Right? And that was the original idea of the original GPUs, like the graphic processing units. It was for graphics. But then clever people found out that, hey, that's more or less matrix operations. And we have a ton of matrix operations when it comes to the physics around us, to solving partial differential equations, systems, right? Like Navier-Stokes, for example, or Euler, etc. Right? So then clever people found out that with these GPUs, the original ones, you could even solve discretized linear systems, so partial differential equations turned into linear systems of algebraic equations, much faster. Right? I mean, and NVIDIA then brought it to perfection, that now the result is really that you have applications like in molecular modeling, for example, where you have these huge macromolecules as a basis. Then that you get easily a factor of 100 speed up between these GPUs and the CPUs, the central processing units. Mm-hmm. I mean, you could look at these cores. I mean, these have thousands of cores, right? And each core is like a central processing unit, right? But very specialized towards solving matrix-based operations, right?
Mm-hmm.
Yeah,
very interesting.
And yes, you are right. I mean, we are now using these days. We are using GPUs more and more, also for high performance computing, mm-hmm. right? For especially for the solver part of these, huge simulation codes with millions and millions of lines of computer program, so the solver itself has a very time-consuming core, and this time-consuming core, then or compute-intensive core, solver, then speeds up nicely, usually between 5 and 20 or so, yes, so that's very, very useful.
Yeah, that was nicely explained.
And we use it also. That's one. That's one of our layers in the container. Is the GPU layer. Mm-hmm. Each base container which we build, is talking to the GPU.
So what I want to walk through is, I've done some research on UberCloud, and we want to go through the steps which you actually do, just to give the audience an impression on how to use UberCloud. So first of all, you obviously choose the size of the cluster, if I'm correct, right? How big can that be, that cluster?
Oh yeah, good point. I mean, the largest so we did in practice is between 500 and 1,000 cores. But because these containers don't consume any performance by themselves, you can go much higher, 10,000, 20,000 or so. That's not a problem, right? And they are usually, if you divide it by, if you take Intel processors, 44 cores or AMD 60 cores or whatever, then divide that by the number of cores, and you have the number of compute nodes you can handle with that. Each compute node then has a container, and these containers are able to talk to each other through InfiniBand. Right?
Yeah. So to touch on that point, what just popped into my head is, could you theoretically do a DNS simulation via UberCloud?
Absolutely. Because I mean, the only requirement is that your algorithm can be partitioned into smaller pieces which can be executed in parallel.
Mm-hmm. Okay.
And that's all. I mean, it really depends on how tightly these individual parallel pieces or distributed pieces, how tightly coupled they are. Give you an example. There are implicit algorithms, there are explicit algorithms, mm-hmm. and also there are like physics-based, molecule-based algorithms, atom-based algorithms, etc., where you follow the path of a particle, for example, particle simulations-based simulations, right? Mm-hmm. They are highly parallel, and those algorithms, they scale up to thousands and thousands of cores, depending, on the size of the problem. Right? The bigger the problem, the more scalable the whole simulation is. Then, but on the other end, if you have implicit solvers, then you have permanent communication because there are, mathematically speaking, algorithmically speaking, there are recurrencies which request tight communication, send and receive during the calculation itself. And those algorithms, the implicit ones, they usually scale up to 16, 32, maybe 64 cores. And then the curve flattens. It's no longer really scalable. So, and that's very important because for our customers, we do benchmarks. We try to find the sweet spot. So, how much can you scale until still you will get a very good price-performance relationship? At one point in time, your curve goes even down. And you want to really know when the curve really starts to flatten. And then you stop. If it's 64 cores, then you certainly don't recommend your customer to use 128 cores, because then for almost the same performance, using more cores which don't serve anything.
Yeah, makes absolute sense. So in the first step, we had how big the cluster is, of course, we covered that. And the second step, we have the cloud instance. For instance, if you choose Azure with H16, whatever. Yeah. Then, and the third step, there is this NVIDIA host, so to speak, you choose, which basically, or it's not chosen, it's basically implemented to have this remote visualization. Is it correct?
Oh, that's a good point. Yeah, that's very important. That's another a challenge originally, or a drawback for HPC Cloud. It was, not really sending the data to the cloud. Usually you have a file with boundary conditions and initial conditions for your physics, whatever. So you send it to the cloud. Usually maybe a few hundred megabytes, but the results you are creating, that can be gigabytes of results. And either you store them first, or what you want to do, you want to work like you are used to work at home or in the office, right? On your workstation. You want to see your immediate results, or you want to even stop after 100 iterations. You want to check if everything converges into the nice direction. Right? So our containers allow for interactive use. So they are able to support you with interactive and with batch. Right? So interactive means, hey, I want to see my intermediate results, or hey, I want to see the final result, like post-processing, etc. And then the host compute node, the host node, you have a cluster with compute nodes and one host node for all the management, etc., etc. And that host sits on an NV6, when you mentioned Microsoft M. So the NV6 stands for, NVIDIA, etc., with 6 compute cores. So this is Intel, but 1 GPU from NVIDIA. And this GPU is able to accelerate your remote visualization with the aid of a software which is called NiceDCV, a company which has been acquired by Amazon AWS like 3 years ago. They have DCV, it's a desktop cloud visualization, and they can produce 30 frames per second, and each frame with 6 million pixels. This is basically real life. Yeah, this is real time, right? Which is very nice because then up to 50 or 100 million degrees of freedom, like finite elements or finite volumes, etc. There's no
lag in between.
Yeah. It's a seamless film, basically animation. Right? Only after that, okay, but that's. So that's, again, this layer is also part of our base container.
That's interesting. So one very interesting project I came across, and also saw an interview with you in the internet on YouTube, which is about the Living Heart project. So maybe you can explain that in a bit, because for me that's super interesting. I have an affinity for medicine a bit, and when I saw that, it was super interesting.
Yeah. So Living Heart Project, yes, and I mean, it's a really complex engineering, physics problems and their simulations. That's my favorite, right?
Yeah.
So, and one of those is the Living Heart Project, which has been started by Dassault with support from the FDA, Food and Drug Association in the US, in 2015. And the aim was really to build basically the digital twin. So very early then, the idea has been born like in 2012, 2013, but you know how it is with these challenging projects. So very early, very future-oriented then. And Dassault Simulia, especially part of that team, with Abacus, developed together with the greatest minds in the healthcare community, so to speak, especially cardio researchers, developed a heart model, very, very complex, and with all the facets of a heart, and together with great minds, for example, from Stanford University and many others. Right? The project these days has about 150 members, member organizations, right? And very famous research and industry organizations being part of that. And but these realistic simulations take a lot of time. So Stanford, for example, Alan Kuhl's department, they said that the arrhythmia simulations they want to do, like they want to check 40 drugs if they cause arrhythmia or not, but not with people. That would be dangerous, but really with simulations. Yeah. And 3 years later, they succeeded. So they checked 42 drugs and found that a few drugs, a handful, sotalol, quinine, and a few others, they can cause arrhythmia if you don't do the dose right. You know? And you simulated it, and the results were identical to the real life results. Usually, so Professor Ellen Kuhl, she said, without cloud and UberCloud in that context, we'd never been able to do this simulation in under 2 to 3 years. And we were able together to reduce this in under 1 month.
That's crazy.
And this, exactly, right. But we used a ton of resources from our partners like Advania, for example, the cloud provider in Iceland. And the whole thing has been nicely supported by Intel and HPE. So they were very interested. They are always interested in the greatest applications to get to demonstrate the power of their own systems, right? Which they are building. And after that, we did 4 different more, and we have 3 more now in the pipeline. Right? It's all so highly complex that no way to do it on like your workstation or a smaller server, which you usually have in your department or so. No way. So you really need very powerful cloud HPC resources to do that. And 2 of these projects have won several prestigious international awards for this kind of simulations. So which is nice. We're very proud of.
Yeah, I can understand that. 2 last things I want to touch upon is one is, what is your vision 5 to 10 years? Maybe not 50, but 5 to 10 years. And also in terms of AI and the digital twin off the shelf, what would you say about that?
Oh yeah, so that each answer can easily take an hour. So I do. No, it is very difficult because, especially in our IT community, new developments, innovations, they are now going so fast that we are currently doing things which I've never thought of, even 10 years ago, right? So digital twin is a great keyword which you used. I can see that in a few years, like in a handful of years or so, every simulation you do will be part of a digital twin. Right. So whatever you produce, or you study, you will have a digital twin. Be it a human or an animal or whatever, or a machinery. Right. The digital twin is always like running in parallel to the real thing. It's the key to a successful personalized medicine thing. Right. Operations will be done with the personalized digital twin of the patient. Doctors will sit around a screen and simulate the operation before they really do the very challenging same thing than in real life. Right? Also, currently drugs, everybody gets the same drug. Right? But the symptoms and the people, the personalities, they're all very different. So finding the personalized medicine with the personalized dose, right, to avoid overdosing, etc., right, it will be very natural. Right? And also, what we have seen with our Living Heart project, for example, we worked with doctors already, medical researchers who are not familiar with high performance computing, but with a container and just having direct access into your container to this real workflow makes almost HPC available to everybody without having to know about HPC. Yeah. Right? You need to know the knobs of your software to steer it to the right result still. And that's what we call democratization. So that it's already now a big thing. Right? Many organizations, like Revolution in Simulation, for example, or ASES or NAFEMS, sorry, they are all moving and pushing nicely towards democratization of high-performance computing.
That's very good that you mentioned also.
And by the way, the other keyword you used, and then you have to stop me, is AI. Right? We already had a few real great projects where we were able, with OpenFOAM, for example, to speed up a simulation with deep learning, TensorFlow, etc., by a factor of over 1,000.
It's crazy.
So, instead of hours, you are now under 5 minutes. Yeah. Right? And get the result. And things which you can do in 5 minutes, you can basically do in real time with deep learning and variants of deep learning. Now they are all getting better and better, right? Yeah.
It's good that you mentioned the democratization, because only, as far as I know, 1 in 25 engineers have access to simulation. So we have to make the step to go towards that almost every engineer has access to simulation.
This will be definitely supported, pushed, or requested by 3D printing. Right? 3D printing can already be done by every engineer. Just reading a little bit of the manual and then print something. But ideally, necessarily, you need to simulate before you print, because you need to know the best suited material and also geometries, etc. Right? You need to find the best suited geometry where you need minimum amount of material, and also get the best shape, get the best flow through it, get the best material analysis, or the best material, etc. So that will, from different sides, we are getting towards democratization of CAE or HPC or whatever you call it.
Yeah, very great, very great. The last thing I want to touch on is the horizontal segment of quantum computing. What do you think about that? That will definitely come. Would you say the same thing?
Yeah, so what we see, in fact, so the last 10 conferences or so, which I attended during the last, 2 years or so, they had always a quantum computing component. And so what I see is really they are making great progress. Right? There are now startups which are fully focused on quantum computing in Silicon Valley. So one of them is our customer, where they simulate how this computer architecture should be composed best. And that will definitely come. I'm not an expert, though, but I studied math and physics, so quantum computing makes a ton of sense, but comes with big challenges still. So that's all I have to say about that.
We will see what the future brings. I would wrap things up, and I would say thanks a lot, Wolfgang, for your time. It was an absolute pleasure talking to you about the complex topics, also a little bit easier topics, but you explained it very well to the audience, and I think everybody will understand what UberCloud is, what HPC is, and how a GPU now works as compared to a CPU. And I would like to thank you very much for your time again, and we'll see each other on LinkedIn, I would say.
Yeah, definitely. And in real life very soon, because you're near Munich and I'm in Regensburg, which is just 1 hour. So see you hopefully personally soon again.
Yeah.
Healthy and strong.
Yeah, would be an absolute pleasure, Wolfgang. Thanks again.
Yeah. Thank you. Bye-bye.
Bye-bye.